take it away.
All right, cool. So now we're going to be talking about the robot game, which is the most well-known part of FLL. Eddie, could you go on to the next slide? Okay. So you might be asking, what is the robot game? Each year, FIRST releases a new challenge that is inspired by an overall theme. This year, the theme revolves around fitness and it's called Replay. So on the robot game, you have a field and there's missions laid out on the field. By completing missions, your robot gets awarded points. So the overall goal is to build and program a robot. There's two parts, the robot performance, where you score points by performing these missions. And the second part is the robot design, where you're judged on your robot. So this is what a robot performance would look like in the past, where many teams from a region would gather up at a live event and the robots would compete. However, due to the current situation, it might be different. FIRST has a guideline on their website about how to compete during COVID-19. And the general guideline is that you might have to videotape your robot game and send it in. And the full guideline can be found on the FIRST website. So let's get started with the first part, the robot performance. The robot performance is where your robot actually completes these missions. And each round is 2.5 minutes. So you have exactly 2.5 minutes to complete as many missions as you can. You get points awarded per mission. Each mission is a different amount of points, and you have 3 chances at it. So out of the 3 chances, your highest score gets taken as your final score. So let's watch a robot performance demo. This is actually my robot from the past when I competed on the Dragon Knights FLL team. Cool, so that's a video of a demo of a robot performance. And after that, the second part of the robot game is called the robot design. The robot design is where you bring in your robot to the judging room, and there's multiple judges who will ask you questions, and questions about your game strategy, your design, and your programming, and they grade you based on a rubric. So so that means that throughout the season, you should be documenting your progress. First provides a good example for this through their engineering notebook, although it's targeted more towards beginner teams as it's very structured, but it's still a great place to go off of. And you don't have to use their engineering notebook. You can always make your own. So what does the robot design look like? I'd like to invite team 32072, the Cyborgs, who placed second place in robot programming at the state competition, to show us a robot design demo.
Good afternoon. We're team 32072, the Cyborgs. We're currently a team of 7 members, but the other 5 couldn't make it this time. I'm Simon, and the person who will be presenting with me is my teammate, Leo.
Okay, so for our base robot design strategy, we created a box design so it could wall score and also have drop-on attachments. For our mission selection priority, we did traffic swing and elevator in one run because they were close together, design and build because it was both close to base and gave a lot of points, crane and safety factor together because they were close together, and elevated places. We also got the small area advantage. For the game plan, for game 1, we wanted a more secure and reliable run, and for game 2 and 3, we wanted to be more challenging and vicious for points. And for the design iteration, we used an agile scrum design cycle, which put simply is where you create a prototype, get feedback, and then create a better version of that prototype.
This is our base robot design. The picture on the left is what it looked like when we were working on it. Of course, there's many loose cables which we had to organize in the final product. So when we went at the year, we decided we wanted at least 3 outputs. An output could be something like a gear rotation. We have 3 large motors. 2 of them is for the robot's 2-wheel drive. We have 1 large motor for attachments with 2 outputs going off of it. And we also have a medium motor crammed in at the front. So in total, aside from the wheels, we have 2 motors, which results in a total of 3 outputs. We wanted more outputs because the more outputs you have on your robot, the more gear-powered attachments you can have, generally speaking, which means that in a single run, your robot has far more potential. We also have 2 color sensors, which allows us to do far more than a single color sensor, meaning you can follow a line in ways that a single color sensor can't do. We also have a gyro sensor. A gyro sensor essentially measures the degree of rotation. In our first 2 years, we found that manually turning the robot via motor rotations was extremely unreliable. So with use of the gyro sensor, it means the robot stops once it hits a certain angle, and that makes turns far more reliable on EV3. In our previous years, our robot also broke down quite often on the inside, so we decided we wanted a removable lid. A removable lid for us made the robot far easier to repair. We also utilized O-frames quite often in design, as O-frames, being frames, are considerably stronger than conventional beams. We also have flat tops and sides. A strategy we used quite often during the robot game was wall squaring, where the robot leans itself against the wall and then it positions itself. This allows it to align either the latitude or the longitude simply by going against the wall. We used wall squaring quite often as it was an easy way to fix out human errors made during the robot launch.
So for our design and build mission, we used the agile scrum strategy that I stated earlier. For our first prototype, we had this frame that simply pushed these stacked blocks into the circles, but this was extremely unreliable, as if you weren't going at extremely small speeds, the blocks would simply topple over. So we created this frame that held them in place, meaning you can go faster and not have the blocks topple over. But we realized that this didn't give us any points at all because no part of the robot can be touching the blocks when they're inside of the circle, and this counted as part of the robot. So we later realized that as long as they're touching each other, we could get the same amount of points as if we stacked them up upon each other. So we created this frame that basically pushed these blocks that were laid flat on the ground into the circles.
This highlights the importance of reading the challenge very thoroughly. We also used the gyro sensor. This year, there are multiple easy point grab missions in the housing units, which you could stack correctly and push into the circles. For this, we used the gyroturn as we measured before. This made the program far more reliable than when we did it with motor rotations. In our first 2 years, we found that programs quickly got cluttered and such. When we made a change, we didn't know where that change was made. We often forgot. And after a while, it was made extremely hard to debug the program. Therefore, we decided to use EV3's built-in comment features. Whenever we changed a value in the program, we wrote down the previous values in the comment, so if we ended up making the program worse, we could always revert it to the original value. We also used these strings to space apart blocks. These 5 blocks right here do the exact same thing. Well, they don't do the exact same thing, but they perform the same function, which is that they all contribute towards a gyroturn. We use this string right here to group them apart from these other 2 blocks to show that this does its own thing, then this does its own thing, and this does its own thing. These measures taken in the program made it far more readable and far easily to debug and fix.
So for our elevator mission, you would have to, originally the blue block would be facing upwards and this beige block would be facing downwards, and you would have to make it so the blue block is facing downwards and the beige block is facing upwards. So I use this attachment, which is literally just a part that extends off the robot and would push the elevator downwards. And for the traffic and swing mission, we also used the agile scrum strategy. We started off with this elevator that didn't use any motor at all to this elevator that actually used a motor and was drop on, but we realized that we were overthinking the problem and that we could just use this shoving attachment where it would slide under the mission and force it up against the wall, then simply drive forward, releasing the swing, and then jolt backwards, disposing itself so it wouldn't get in the way of the elevator mission.
This means that then in a single move forward, we did 2 missions at once, and then the robot backs up, leaving the attachment behind, which is allowed by rules, and then wall squares to align the latitude, and then goes on to complete other missions.
So for the crane mission, we use this simple attachment. To this longer area would push a blue block into a circle, and then this white part would push these blue levers so it would get the correct angle and then drop the block on top of the blue block that we pushed in before.
In our first years, we also found that it was extremely difficult to organize all of our programs in the actual files. In the EV3 GUI, especially if you start using MyBlocks quite often, it gets extremely cluttered and hard to navigate. This means that in the game, while you're trying to find your program, you're wasting valuable time. So thanks to an idea from Anthony and help from him, we made use of the sequencer. The sequencer basically creates a little user interface in which you can cycle through slides with the EV3 buttons, and once you're on a certain slide that's attached to a certain program, you can click it and that program will run. We saved all of our 4 runs into MyBlocks, and we saved those MyBlocks into the sequencer. The sequencer saved valuable time on the game map as we were easily able to find and cycle through our programs.
And this is our team motto. Thank you for listening.
Okay, thank you to Team Cyborgs for that robot design demo. Usually after you present, the judges may ask you some further questions about your robot. So now let's move on to actually making a great robot, and I'll break this down into 3 parts: strategy, hardware, and software. First off, let's start with strategy. Strategy is probably the most important, and you should be doing this before moving on to actually building your robot. So for strategy, you want to zone your missions. So on each run of your robot, you should be doing multiple missions at the same time. And you can take a picture of the map and draw out and plan out which missions you're going to do per run. And you want to pick missions based on their location and their type of action. So some missions you have to navigate, push, retrieve, press, raise, deliver, or flip objects. So missions with similar actions can be done together with the same part of your robot. And you only have 2.5 minutes, so you shouldn't be doing all of them. Instead, pick the ones to maximize your points. For rookie teams, you want to focus on easy missions And if you don't feel confident enough to do multiple missions at the same time, it's perfectly fine when you're just getting started to just do one mission per run. So the second part is hardware. For the controller, motors, and sensors, we have two possible choices you can use, which is Spike Prime and EV3. I'd recommend most teams to use EV3 as that has been around for a lot longer, so there's much more documentation and like YouTube tutorials on using EV3. Spike Prime came out about a year ago, so it's on the newer side, and it's a bit less expensive. However, the controller only has 6 ports, while the EV3 controller has 8 ports. The other difference is that the controller for Spike Prime has a gyro built in. But for most teams, I'd recommend sticking with the tried and true EV3 system. For rookie teams, I recommend you guys start off with a simple robot design, like pictured on the right. So you have your base robot and you have small attachments you put onto the robot, like a lever or a grabber that does certain missions. These are pretty easy to make. And if you really don't know where to get started, there's plenty of online tutorials and you can get started from those. For an advanced robot design, this is what most teams use, is a multi-part robot where you have the chassis. The chassis is the base where you place all your motors and sensors and of course the controller. It has a lot of attachment points for your different attachments, and it has to be strong and durable, of course, so it doesn't fall apart easily. And then on top of your chassis, you should have multiple attachments and they fit on easily and you should be able to take them on and off easily, and they're made to do specific missions. So this was my robot from when I competed in the Animal Allies FLL challenge. On the right, you can see the chassis, the top view and the bottom view. On the bottom, we have 3 color sensors for detecting lines. In the middle, you see our first attachment. And at the right, you see how it looks like when we put on the attachment onto the chassis. Here's a couple more examples. So one thing you notice about these robots is that they're very rectangular. This is great because there's walls around the field, which makes it easy to line up against the walls to make sure you're exactly perpendicular to them. Additionally, if you look, there's motor connections on the top. These are for attachments. So when you put something on top, you can transfer the rotation of the motor onto your attachments. And one thing the gears might look a bit weird, and I'll explain that on the next slide. So gears. Gears are probably one of the most important mechanisms you can use as they transfer motion. On the left, you see the most common gears, but on the right is something called the dog gear. The dog gear is used by many FLL teams. If you look on YouTube, you can find tutorials on how to make the dog gear, and it makes transferring motion super simple. So it connects super simple. You don't have to worry about the gears not lining up. Here are some more useful mechanisms that you might use on your robot. The first is a one-way door. These are really useful for picking up things, as a hoop can go in, but it can't come out, so you can grab onto it. The middle one is a grabber. It would be powered by a motor, and it allows you to grab things or drop things. On the right, there's a rack and pinion. This allows you to convert rotation into linear motion. This year, I might recommend some teams who can't meet up in person to work on the physical robot. You might want to try out a 3D modeling tool. I personally did not use one during my season, but I've seen that a lot of teams recommend a free software called Studio 2.0, where you can put together your robot on your computer without actually having to build anything physically. Here are some final tips while building your robot. You want to have redundant reinforcement, which means multiple pegs per connection so they don't come apart easily. Of course, you don't want to use too many, as that can make your robot too heavy. Additionally, you want to have appropriate balance, so your robot should be symmetrical. And simplicity is also important, as complex robots are cool, but A lot of times, the more parts you have, the more likely something would go wrong during a run. And finally, accessibility is important, as you should be able to change out the batteries in the controller easily or get to the charging port if you're using a battery bank. And in case you need to replace a sensor or anything, your robot should be easy to access. And as always, Google is your best friend, and there's so many tutorials and past robots you can find on YouTube. So go on YouTube, search for FLL robots, and you can get tons of inspiration from past ideas.